Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into 3.6 in the Big Ideas Math Integrated Math 1 textbook on transformations of graphs of linear functions. This is the final section in the chapter, so after this comes the review and the Chapter 3 tested and cumulative assessment. This section is interesting to me, and I don't know how many of you guys are assigned problems out of the textbook for this from your teacher, instructor, what have you, because this can be a little highfalutin. Now, I understand, I acknowledge, and I kind of even appreciate why Big Ideas Math actually sticks this section here the way that they do. Given how much they heavily emphasize, and keep in mind, I've already recorded videos for IM2 and IM3 textbooks, so I'm well aware of this. Given how heavily they emphasize transformations as a whole, it totally makes sense that they do this, that this is an introduction of what this stuff looks like. I do find it to be a little highfalutin for the fact that you've just learned function notation, you've just learned slope-intercept form and standard form and things like that, and suddenly you're taking something on linear equations and you're not doing something different with them, but you're finding other means for how they can be written, yet you're jumping into these other ones. There's a third form called point-slope form, and I had to do some digging. We're actually going to write equations using point-slope form in the next chapter, as well as slope-intercept and standard form. But we're not going to graph out a point-slope form, and I don't even know how much graphing we're doing in this section. Here we're learning and understanding and describing what transformations are, and I almost feel like if I do too much over-teaching on this one as opposed to just saying things how they are, it might break you a little bit because you're just hearing words, and I don't think it's going to come out the right way. I think that it's not necessarily the fault of where you are at in IM1. I also think it's the fault of linear equations. See, linear equations are just a line, and if I do... What we're doing on transformations, guys, is we're translating them. We're moving them up and down, left and right. We are vertically stretching them or horizontally stretching them or vertically shrinking them. See, and here's the problem. Everything I'm saying, you can't do with a line. A line is an all real number domain. You won't be able to see the characteristic. Oh, and you'll flip them over. You can see that one. You'll see the translations sort of, but you won't be able to see them how they are compared to something like a V-shaped graph. I can understand what it means to translate this up and down where this point is going specifically. When this thing shrinks this way and when it flips over this way, those are things you can very clearly see. And I'm making this introduction the way that it is so you're understanding that we have a 67 problem set, and with the lecture, I think I'm just going to lecture. I'm going to let the lecture say what it has to say, and we're going to do the problems based on what the lecture has to say. I think that that's our best way to go through this. This solution guide is going to be, I'm going to explain why the things, why the lecture thing justifies what they do, but outside of that, I don't think we can get into deep detail. Not until you're in IM2 and IM3 and you understand function notation more and you've done a lot with these other kinds of graphs and you're going to be doing it a lot more. And that's the last thing I want to state about this. I don't think we're going to talk about transformations again in this book. So this is kind of just a good segue into what you'll do in IM2, but then it's not really seen again outside of this chapter. So that being said, guys, this is the longest intro I've ever done, but jump down in the description section down below if you'd like to find a PDF of this particular section, as well as graph paper if graphs are needed. I think we're taking graphs and information and describing transformations. I don't know if we're actually doing graphs themselves, but let's go take a look at what we have here. We are going to translate and reflect graphs of linear functions. Translating was the one where I said you take this graph and you move it. You move it left and right, you move it up and down. A reflection is taking this thing and, say, flipping it up and down like that. That's a reflection, flipping it over. Now, did I flip it over up and down or did I flip it over left and right? See, you can't really tell. You can't really tell, and that's part of the point of when it comes to linear functions that it's kind of iffy to talk about, but we are going to be doing those. We're going to stretch and shrink graphs of linear functions, and that's, again, slope. We'll talk about slope. And we'll combine transformations of graphs of linear functions. That means do a combination of maybe translate and reflect, maybe translate and shrink, maybe reflect and stretch, those things all together. A lot of new vocab here. Family of functions is the first thing they're talking about with parent functions here as well. And then what are the different types of transformations? We have all of these different types of transformations here. So translation, reflection, shrinks and stretches. Sometimes instead of the word shrink, I say the word compress. So I'll say something's a compression. So just make sure that you're aware of that. Okay, guys, a family of functions is a group of functions with similar characteristics. You've heard the word linear before. any such linear functions are all within the same family. You've heard me say the word quadratic. I don't know if you know those are the U-shaped graphs. Those are quadratic functions. Absolute value functions have that V shape. Those are within their own respective families. They have different families. The most basic one, the most basic function in a family of functions is the parent function. This is the one that is completely untransformed from the most, again, they said the word basic. The slope is just a 1, up 1 over 1 slope. Y-intercept is just 0. Y equals x, f of x equals x, y equals x. That is y equals 1x plus 0. That's the parent function here. No transformations applied to it. The graphs of all other non-constant linear functions are transformations of the graph of the parent function. So when they say non-constant, they want to be specific that it needs to have the x in it. You can't have a slope of 0 for us to talk about how we're going to do the transformations that we do. Transformation changes the size, shape, position, or orientation of a graph, and we're going to see all the different varieties here. A translation, I stated a couple times, it shifts the graph horizontally or vertically, but does not change the size, shape, or orientation of the graph. Now, I want to remind you that all these functions, they have an infinite domain and range. The lines go forever in both directions. So to change size is kind of it's hard to talk about, but we're talking about changing the y's and the x's potentially. Now, let's talk vertical translations first, then I'll get to horizontal translations. This says the graph of y equals f of x plus k is a vertical translation of the graph y equals f of x where k doesn't equal 0. Now, to give you a great reminder of this, and of course we're going to have examples, remember y equals f of x says take an original function that you have and substitute that into here. So for example, if your original f of x was, let's say it was just negative 2x. Okay. Now this says y equals f of x plus k. This is y equals negative 2x plus k. Now the k value can represent any number. Well, I guess a non-zero number to be a translation. It can represent any non-zero number, positive or negative. If it was a 4, then this would say negative 2x plus 4. Well, this looks like something you've seen before because this is y equals mx plus b form. This was our last section, right? So what does the 4 do for you guys? It makes it the y-intercept. If your y-intercept was 4, boom, it would look like that, and you do your slope like this. Or if your y-intercept was back to 0, then it would start right here. So that being a translation makes a bunch of sense to us that a plus 4 would bring it up 4 units like that. Now, if it was a minus 3 or something, it would bring it down 3 units. So this is the example of a vertical translation. Vertical translation of this, taking whatever graph you have. The slope doesn't change. The slope is whatever it is. And then that y-intercept is where we start. So I think we can understand a plus k outside of whatever your original function is, translating your graph just by adding or subtracting a certain amount. Horizontal translations are going to be really, really tough for us to grasp. So I'm just going to say it as it's said and see if we can follow along. It says the graph of y equals f of x minus h is a horizontal translation of the graph of y equals f of x where h doesn't equal 0. Okay, the tricky parts about this are number one, the thing inside of here is affecting your entire function. Now, this means this would take place of x wherever it was. Remember when I said the equation was f of x equals, and I know I'm doing examples before the examples, but you know where it said f of x equals 2x, that means f of x minus h. We've done function notation before. We plugged in numbers for x, but you can plug in anything for x. I've even said if it says booger, you can plug in booger for x. You can also plug in x minus h for x. And with substitution, when in doubt, use your damn parentheses. So this would be 2 times whatever x minus h is. So that's number one. It actually takes place of x, and it substitutes in parentheses as that quantity. That's one tricky part. That's how function notation is being applied. Number two, it says minus h. Remember how this said plus k, and I said plus 4, you go up 4, minus 4, you go down 4? This says minus h in the formula, and yet they said h is the amount that you go, when it's positive, to the right, whereas when h is negative, this is how much you go to the left. When h is negative, that's how much you go to the left. But when h is negative, subtracting a negative becomes addition. Subtracting h from the inputs before evaluating the function shifts the graph left and right. And h has the opposite sign. It's the opposite sign. Whatever it says inside of there, you do the opposite of. And we're going to see these examples in full. So horizontal and vertical translations. Let f of x equal 2x minus 1. Okay, here's our new function, f of x equals 2x minus 1. We should know how to graph that based off the y-intercept. We have it in black right here. The y-intercept and the slope up 2 over 1, up 2 over 1, etc. Here's our original. Graph a new function g of x. You can see how function notation is being utilized. This is y equals this and y equals that, but we're saying they're two different y values. Graph a new y value, y equals, g of x equals, f of x plus 3, and t of x, there's another new one, equals f of, and in parentheses, x plus 3. Describe the transformations from the graph of f. Now, we actually have to graph these. Describe the transformations from the graph of f to the graphs of g and t. Okay, so we take our original f of x graph, which is in black in both examples. In blue is the new g of x, in red is the new t of x. Now, what did they do for these ones? You can notice that based off what they described previously, an f of x plus k means it's a vertical translation. This has a k value of 3. That means this is going to take whatever function it is and shift the values up 3 units from where they were. It's a translation up 3 units. Instead of this point being right here, it's now going to move up 3 units, 1, 2, 3, to right here. Instead of this point being right here, it's going to move up 1, 2, 3 to right here. And this point down here is going to move up 1, 2, 3 to this point right here. So every point is moving 3 units up from where it was before. Now, I'm sure we're going to do more with the information, and I'm sure I'm over-speaking on it, but I just mentioned it before. This means I can substitute 2x minus 1 in for f of x, and we can do that plus 3 right there, and negative 1 plus 3 is 2. Do we agree that this graph is the equation y equals 2x plus 2? We got a y-intercept of 2 and a rise of 2 run in 1. I believe it does look like that, so I agree with that. Second one gets a little bit trickier because this says f of x plus 3. Now, our formula said f of x minus h. The fact that the formula shows a minus and this shows a plus must mean we're subtracting a negative number. They said it's in this form here, therefore our h value is negative 3. We're subtracting a negative 3 for it to appear like a plus in here. That's the tricky part about being inside the function. You do opposite of what it shows. Therefore, we're going to translate all of our points 3 units to the left, not to the right, but to the left. And that's it. First of all, it's a horizontal translation. Second of all, we go opposite of what it says in there. We go 3 left. So this point is going to go 1, 2, 3 to the left, like so, and it's right there. This point will go 1, 2, 3 to the left, like so, right there. And this point here, 1, 2, 3 to the left, right, like, you know, et cetera, et cetera, et cetera. So now this new graph, let's see if I substitute, and again, I know I'm over speaking on it in the way that they're probably going to talk about it later. So then I get to say, all right, cool, we already talked about it, and there are the examples. Y equals, now here's your function. It says f of x plus 3. Remember our original was 2x minus 1. I'm going to write 2x minus 1, but instead of x, I'm going to write x plus 3. And then minus 1. Notice it's in parentheses. If I distribute 2 to the x and 2 to the 3, I get this. And that means it's y equals 2x plus 5. Was this red graph the line for y equals 2x plus 5? It actually is. Take a look. The y-intercept's at 5. And although you can't see the window going up 2 over 1, you can go down 2, left 1, and the slope's the same. So this is that equation. So these are working out the way that they're supposed to. Now again, I can't speak too much on this thing without overcomplicating it. So I'm not going to, but remember, you flip the sign for this, and anything inside the function affects horizontal business, not vertical business. Anything outside the function affects y, anything inside the function affects x. Okay. A reflection is a transformation, I'll keep myself here. A reflection is a transformation that flips a graph over, called the line of reflection. Now you're going to learn more about transformations as a whole, including translating reflections, all that. You're going to learn that more in the geometry stuff of IM1, or whenever you do all the things. I think it's later in the book. But reflection is flipping something over. And so you might know the phrase line of reflection later, more so when you do more on reflections. But this one has a clear reflection. When you look at black and red, they're reflecting across the x-axis. That means that this x-axis is the line of reflection for black to flip itself over and then become red, like so. And then in this one, they're reflecting over the y-axis. You can see in the y-axis, there's a mirror image of black to red, like so. And when you look at the two equations, I see a negative outside of the function. This is negative f of x. So anything there is going to affect something vertically. That's why it's flipping over this axis. See, the x-axis is a vertical flip. So a vertical flip means it's affecting the y values. Whatever a y value previously was, it's now flipped over and it's become a new y value there for the same x. F of negative x means it's affecting things horizontally. It's flipping things over that way. So whatever was some x value right here is flipped over the y-axis and has now become this value here. The x value has changed. Kind of looks like a smiley face. The x value has changed its sign from a 5 to a negative 5 or something like that. And those are the flips of those. Multiplying the outputs by negative 1 changes their signs. Multiplying the inputs by negative 1 changes their signs, depending on what you have. So reflections in the x and y axis. Here's a new function. We're going to let g of x equal negative f of x and t of x equal f of negative x. Now what we're going to look at here is a table of values, and we might have to do some of the same things if we're not, I don't know if we're sketching our own graphs or not. It says graph them. But they're using a table of values here to explain away what's happening. The original xy table would probably have looked like this for y equals 1/2 x plus 1. And notice how they're choosing values of x that are by increments of 2 so they can divide by 2 easily. Half of negative 4 is negative 2. Negative 2 plus 1 is negative 1. Half of negative 2 is negative 1. Negative 1 plus 1 is 0. Half of 0 is 0. 0 plus 1 is 1. Okay, so those are points on the table. You can graph that 1 in black right there. You can also graph it by knowing you're up 1 over 2 or down 1 left 2, etc. Right? What we're going to do is we're going to flip this thing over. We're going to change the y values. If f of x was negative 1, 0, and 1, well, f of negative x is 1, 0, and negative 1 for the same x values. So what happened? Whatever the y values were before, they flipped over. It was here at negative 4, negative 1. Now it's up at negative 4, positive 1. So it flipped over. That was our reflection. Same is true on this one here, except now we're doing f of negative x, which means we have to take whatever x values we would have done and flip those over to now figure out how those y values compare. Previously, we would have had this x and this y right here, and notice that they're picking different values out. So, oh, I'm sorry, that's f of negative x. I'm sorry, they're not showing you the original y. So these are some original x values to plug in. They're flipping them over. And then they're plugging those values into here and seeing what they get. Half of 2 is 1, plus 1 is 2. Half of 0 is 0, plus 1 is 1. Half of negative 2 is negative 1, plus 1 is 0. Now you might be wondering, well, how's that any different from plugging in that negative 2 and 0 and plugging in that 0, or like whatever, plugging that negative 2 and getting 0 and plugging that 0 in and getting 1. How's that different from here? The difference is we're not using these x values. We're using these x values up here. We're still using this negative 2, but we're going to plot this one right here for the reflection. So now there's going to be a point that's negative 2, 2. You can see it right there. And 0, 1 is still the same point as before, but 2, 0 is another point right there. This red is a reflection of the black across the y-axis here, where previously you would have plugged in 2 to get 2. Now you plug in negative 2 to get 2. Before you would have plugged in negative 2 to get 0. And now you plug in 2 to get 0. You're plugging in the opposite x to get the same y as you would have before. And that's what that means. Okay, stretches and shrinks. This can be really tricky. And listen, sorry, actually before I move forward, even going back, the translation stuff is a little tricky as well, because as much as we saw these things go left and right, you could have also said, but Mr. Robinson, couldn't we have also moved up to make the black the red? Yes, you could have. Now, it probably would have been a different explanation of what you do with it, but yes, you could have. Linear equations happen to do that. The flipping over is probably unique to what you have to do here. It all depends unless you do a combination of transformations. But stretches and shrinks as well will be a little bit tricky outside of what you know on slope. Because if I horizontally shrink something, that also means I can also vertically stretch that same thing. So it can be a little tricky. You can transform a function by multiplying all the x coordinates by the same factor, a, just some number that a is representing. When a is greater than 1, the transformation is a horizontal shrink. Oh my gosh, you know what? They're explaining this out of order. I'm going to start with the verticals, okay? If we do horizontal first, you guys are going to be so lost. So here we go. You can also transform a function by multiplying the y coordinates by the same factor, a. When a is greater than 1, the transformation is a vertical stretch because the graph stretches away from the x-axis. And that's true. When you multiply by a number more than 1, I'm not even talking about graphs. Take the number 3 and multiply it by a number more than 1. Multiply it by 2, multiply it by 10, 100, or 1.5. Any of those numbers become more than 3. Therefore, it became stretched. Furthermore, as we know that our original parent function for slope-intercept form is just y equals x, the slope of 1, we know that any slope that's bigger represents a steeper, any value that's steeper for slope represents a steeper line. steeper the line. So the bigger the slope, the steeper the line. We recognize that also for vertical bits here. When a is between 0 and 1, you have what's called a vertical shrink, also called a vertical compression, because the graph shrinks toward the x-axis. When I multiply 4 by 1/2, the number doesn't get bigger, it gets smaller. It turns into 2, right? Multiplying by a fraction kind of becomes division. You know what I mean? Multiply by 2/5 becomes something smaller. And we also know that for our slopes, because we know a slope of 1/2 means up 1 over 2. Up 1 over 2 is less steep than up 1 over 1, right? Up 1 over 1 is more of a 45-degree angle. Up 1 over 2 is more of, I don't know, something, right? But so a different kind of angle. So we understand that that's a vertical stretch and a vertical shrink. Notice they're not talking about A being negative because that's being applied to reflections. Now, when A is -2, it does flip over and it does stretch. That's a combination of transformations. We'll get into those. But notice that they're not talking about those. They don't care about those for that. They also don't care about 1 because that's the original parent function. They don't care about 0 because that would be because we're looking at non-constant linear functions only. We want our x to be affected, or y to be affected by x. Now let's go to the horizontal one because this is where it can get confusing. If a is inside of your function, such as like this one right here, now the bigger that a gets, the more that you horizontally shrink your values. It's the same way that x minus h applied. The x minus h means you take opposite of what's inside of there. So when a is bigger than 1, you actually horizontally shrink. Reason I'm not going to speak big on it, it's because your x values need to be, say if a is 2, your x values need to be half of what they were before. When a is between 0 and 1, like a fraction, that's when you get a horizontal stretch. So remember, anything inside of the function, you have to do opposite of what's affecting it. If there's a 2 multiplying to your x's have to be half the size. If you're subtracting 2 from your x's, you have to increase your x values by 2. Those kinds of things affect the horizontalness, and that's where it can get very confusing. Especially because that's also not the same thing as slope, not initially, at least. So when you look at what's in black, the original parent, well, a function, an original function, we can, let's start with the verticals. An original function here, you can vertically stretch it. You can vertically stretch something by multiplying it by a, by the function. That means it's going to become, say, a taller version of what it was. When you multiply by an a that's a horizontal shrink by a fraction, it's going to be a vertical shrink from what it was. It's going to have a lesser slope and all. Now, notice the x-intercept stays the same for this particular version of this, and that's because 0, remember this is where you get a y value of 0. 0 times the number still stays 0. So that's not going to change. When you plug in that number for x, you still get 0 for y, even if you multiply it by 7. That's not going to change. Now this one, this is the horizontal stretches and shrinks. This thing horizontally stretches. Remember, horizontal means this way and that way. The red is considered a horizontal stretch when your a value is between 0 and 1. Remember, it sounds opposite of what it would be. But when a is more than 1, it becomes a horizontal shrink. It's fitting itself inward more that way, towards 0. This time the y-intercept stays the same because you're now choosing values for x that need to be different from what they were to keep the same y value as it was. You need to keep the same x value that you had here as 0 to keep the same y value, and shrinking in towards 0 or stretching from 0 still stays as 0. So the y value stays the same. Okay, let's look at some examples, and they're going to use tables with these as well. They say let f of x equal x minus 1, graph g of x equals f of 1/3 of x, and h of x equals 3 times f of x. Describe the transformations from the graph. And you know what? I've noticed this pattern in the IM2 and IM3 books as well. They describe horizontal first. For the life of me, I don't understand why. People will get lost on it. I'm going to start on part B with this example here. I'm going to move myself. I'm going to expand this down a little bit more. Let's take a look at, once again, f of x equals x minus 1, and let's make it 3 times bigger than it was before in y. The y's will get tripled. If I plugged in 0, 1, and 2 for x into this equation, x minus 1, 0 minus 1 is -1, 1 minus 1 is 0, 2 minus 1 is 1. I'll get these x and y values out. There's my black graph right there. Let's vertically stretch this black graph by a factor of 3. Let's do that by multiplying all our y values by 3. -1 times 3 is -3. 0 times 3 is 0. There's the x-intercept staying the same. And 1 times 3 is 3. So now, instead of this point being right here, just 1 unit away from the x-axis, now it became 3 times larger. Now it's 3 times away from the x-axis. It got vertically stretched. Instead of this point being just 1 unit away from the x-axis, now it's 3 times bigger, 3 times away from the x-axis. This point is 3 times away from the x-axis, but it's on the x-axis, so it's going to stay where it was. So this thing vertically stretched more. It vertically stretched. This 1/3 inside of the function, we're looking at as a horizontal component to this thing. It's going to be horizontal stretch. Everything's going to become, remember, the opposite of what you see here. It's going to become 3 times horizontally stretched from where it was before. What was black right here from the y-axis is now going to be 3 times further out right here. What was black right here is now 3 times further out right here. And then on the y-axis, it'll stay the same. So what you need to do here, and this is where it needs to be a little bit tricky, you want to look at some x values that are 3 times bigger than they normally would be, because we're going to shrink them 3 times. You're like, wait, I thought you said we stretched them. These are 3 times bigger than what we have to do after. We have to take 1/3 of them to get the same y values as we would if that 1/3 wasn't there. So therefore, we need to pick x values that are 3 times bigger, so when we take 1/3 of them, we can then subtract 1 from them. So these are the points we're still plotting. We're plotting these ones right here, but notice the x values are now 3 times bigger than they would have been. So this input thing, you have to pick numbers that are opposite of what you would have been doing. We're going to take 1/3 of our x values, so we need to make x values that are 3 times bigger than we want them to be. Guys, that's tricky. That's very tricky for brand new IM1 students. It's tricky for IM2 students, but at least they've done a lot of function notation practice before. They've grown into, graphing things in general. They understand the different kinds of graphs they're going to be doing it with, and they're not just horizontal one. They're not just linear functions. Okay, horizontal and vertical shrinks. This one I'm going to spend a lot less time on here. Let's start, of course, with vertical. I do not dare start with horizontal. So we're going to start with this one, the 1/4 times f of x here. Multiplying something by 1/4 means also dividing it by 4. So we can take our y values and divide them by 4 in this scenario. If we plug in these x values into, what was our equation? X plus 2. I plug in these numbers for x, get these values out for y. When we divide them by 4, they become 4 times less than they were before. The y values, that is. So therefore, what was in black before, everything is now 1/4 of what it was before. Case in point, the best one I can really look at for you guys is here's a y value of 4. Now it's a y value of 1. It's 4 times smaller than it was before. So we're shrinking it toward the x-axis that way. Here's a y value of 1. Now this is a y value of 1/4. Here's a y value of 2. Now it's a y value of 1/2. Those are actually literally the values that they show on these ones right here, dividing them by 4. I'm unlikely to use tables if we have to graph. I'm likely to plot the original graph as it is and talk about how they shrink. We can talk about the y values, and then we divide by this, and we get that. I'll probably go about it that way. And I'd much rather, honestly, plug them into the equations. I don't know if they're going to do them just yet. I haven't gone through the lecture portion. So I don't know if they're going to be plugging them in yet or not. I hope that they do, so we can do some unique problems that way as well. Anyway, with the horizontal one, it says f of 4x. In this case here, because that's a 4 inside the function, we have to do opposite of that to our x's. That means we're going to horizontally shrink our x's by 1/4. Excuse me. Yes, we're going to horizontally shrink our x's by 1/4. So what you have to do is say, what did our x's originally look like here? Let's multiply them by 4 so we can figure out what y values we're going to get as a result of those x values. So these are the ones that we're going to be graphing here at -1, -2, 0, 2, and 1, 6, compared to that of -4, -2, etc. Because normally -4 plus 2 would have given you that. But we have to do them at these x values here. So we have -1, -2 as a point right here. And that is horizontally shrunk 4 times more than it would have been at -4, -2. So now the -4 from x is now a -1 for x. And now you can see that it's shrunk that way. Almost pushing on a half hour. Combining transformations. They show steps here as far as which order to do it in. My particular order that I like to do is from left to right, alphabetically. We go to A, and then H, and then K, and you'll be good when it comes to not messing up order of operations. They mentioned to do things inside of here first. I get why they're kind of stating it, just so you don't mess that part up. But doing it later in order is completely fine. You just cannot do a vertical stretch before a vertical translation. Excuse me. You cannot do a vertical translation before a vertical stretch unless the vertical stretch is being applied to the entire equation, function, and you'll see that. And you cannot do a horizontal translation before a horizontal stretch or shrink unless that's being applied there as well. When I do a reflection, I'll do it at the same time as a stretch or a shrink, but I'll say you flip it over and then you stretch it or something like that. We have more to say. Combining transformations. So here are the examples. Graph f of x equals x and g of x equals negative 2x plus 3. Describe the transformations from the graph of f to the graph of g. So the original one is just that original parent function. This is a 1 here and plus 0, and when you sketch those graphs, you'll totally note that. This is up, look at the black graph. Y-intercept of 0, up 1 over 1, up 1 over 1. Now, when we graph this one, negative 2x plus 3, we'll do it like we did, slope-intercept form, in the last section, yester section. Down 2 over 1, down 2 over 1 from a y-intercept of 3. That's in red. That's in red. I don't know what this green graph is yet. We haven't talked about it. Now, they said describe them. What we have to do is make sense of where these things are being affected here. Your x value, your function got multiplied by negative 2. It got multiplied by negative 2, therefore 2 things occurred to it. It got vertically stretched, and it reflected over the x-axis. Those are things we're going to have to state. It got vertically stretched, specifically, by a factor of 2. A factor of 2 means it became 2 times larger. The y values became 2 times larger than they were before. The plus 3 happens after the fact, because remember, order of operations, x multiplies by the negative 2 first, and then 3 gets added. The plus 3 is like your plus k. It becomes a vertical translation 3 units up. So if I were to take my, that's what the green graph's for. To take my black graph here and turn it into my red graph, if you literally wanted to do it, you could take it and you could flip it over. All right, you could take this and you could flip it over. There's the reflection. You could stretch it 2 times taller, and that's the green graph. And now we can take the green graph and translate everything 3 units up, and that becomes the red. So do you have to do all those specific steps? It depends on what they require for us in the problem set. We have 67 problems to do. I hope we don't have to do it that many times. Otherwise, this will be way too long of a video. Anyway, there's the graph there. I'm going to move on. These are still lecture problems. Solving a real-life problem. A cable company charges customers $60 per month for its service with no installation fee. So $60 flat rate. So the cost to a customer is represented by C of M equals 60 times M, where M is the number of months per service. To attract new customers, the cable company reduces the monthly fee to $30 instead of $60, but adds an installation fee of $45. The cost to a new customer is represented by R of M equals 30M plus 45. And hopefully you can understand why the function is what it is versus what it was. It went from $60 a month to $30 per month, but now $45 installation fee, where M is still the number of months of service. Describe the transformations. Okay, so the things we can describe on this are, it went from 60 to 30. Oh, they're taking half off, and they are. So to us, that's a vertical shrink. It's a vertical compression. Our cost vertically, because our cost is like our y, our cost has become half of what it was before. So we would say that, well, let's see. I don't know if they describe them as, here they are. Vertical shrink by a factor of 1/2. That happens. But something else happened. This 45, this plus 45 here is something that happens outside of the function on that shrink, right? First, they reduce things by half, and then they're adding a $45 thing on top of it as a flat rate. They didn't add 45 first and then divide it in half. Otherwise, the 45 would be divided by 2, but the 45 is not. So 45 is this flat rate, this installation thing, not dependent on the number of months of service. You pay that regardless for this cable company's new standard. So half of the new function plus 45, and then I don't know if we need to graph it, but if you look at the graph, the original graph is the 60M right here, up 60 over 1 kind of slope, y-intercept of 0. We take half of it, now that's the blue graph, that's up 30 over 1, and then we shift everything up 45 units. Notice these y values are changed in scale, but everything's going up 45 from where it was before. So the red is the new graph compared to black, which shows cost of service based on number of months. Now, initially, you spend more up until some point. You spend the same amount, and then ultimately, you would spend more in the black version as you'd increase the number of months, 2 months and such onward. So I think they're still reducing costs. It's just there's an initial cost there. But a vertical shrink by a factor of 1/2 and a vertical translation 45 units up. That's what that plus K, plus 45 is all about. Okay. Longest lecture there, guys. We're going to get into the vocabulary and core concept check 1 through 4, and then we have numbers 5 through 67 to still do. A lot of transformations to be had. Okay. Number 1, describe the relationship between f of x equals x and all other non-constant linear functions. So f of x equals x is the most basic version. I'm just going to write it right here. It's the most basic version of a linear function because it doesn't have any transformations applied. It doesn't have any reflections. No reflections. It has a slope of 1 and a y-intercept of 0. So those things, we just start at the origin. We go up 1 over 1, period, right? We don't go up 1 over 2. We don't start at the y-intercept of -3. We're not going down for our slope, nothing like that. It's just the most basic version of it. That's number 1. Number 2, name 4 types of transformations. Give an example of each and describe how it affects the graph of a function. Clearly, they didn't give us enough room for this, so I'm just going to blank out what's down here because I'm going to have a new slide for the future problems anyway. So let's blank out what's down here, and let's do our number 2 down here as well. So for number 2, one type is a translation. We can translate, we can shift graphs left and right, or up and down, or up and down. Left, right, and or up, down. I don't even know what I wrote. I don't know what I wrote anymore. That's one of them. So there's one of them. Next one will say, hold on, let me align these well. Next one is reflection. Reflection. We can reflect graphs, or flip, let's see, I'm gonna use different words. We can flip graphs over x-axis or y-axis. When we flip over the x-axis, that's actual a vertical reflection, and over the y-axis is actually a horizontal reflection. We can vertically stretch or shrink, which we still use those words, at least I sometimes use compress, whatever, but affect y values by a factor, by a factor, which means that they become some number of times larger or smaller, and we can horizontally stretch or shrink, which we affect the x values by a factor. Now, it doesn't include the negatives, right? The negatives are what make something reflect. So a negative change on something is not a stretch or shrink. That is a reflection. That's a flip. Number 3, writing. Let me put this a 1 right here. Number 3 on writing. How does the value of a in the equation y equals f of a times x affect the graph of y equals f of x? How does the value of a in the equation y equals a times f of x affect the graph of y equals f of x? Well, the a times f of x is much easier to say. You're taking your value and multiplying it by a, and therefore it affects your y value. Therefore, for y equals a times f of x, like that, is vertically stretching or shrinking y values by a factor of a. Like that's not a cliffhanger of a sentence. I'm literally saying by a factor of a. I'm going to write the next one above here. Y equals f times a of x, or times f of a times x, I should say, is horizontally stretching or shrinking. X values. Now, by the opposite factor, you have to flip this over by a factor of 1 over a. Whatever a was, you need to completely flip it over. If a was 2, guess what? Now you're stretching, or now you're shrinking by a factor of 1/2. If a was 1/3, guess what? Now you're stretching by a factor of 3. So you're doing the opposite whenever it's inside the function. Number 4, the functions f and g are linear functions. The graph of g is a vertical shrink of the graph of f. What can you say about the x-intercepts of the graph of f and g? Is this always true? Explain. Well, what we note, and actually they're giving you a graph right here to explain it. So the x-intercept here you can tell is the same, and I explained why before. The reason for this one, so it's going to stay the same. The reason it's going to stay the same is because you're multiplying 0 by a number, and 0, because the y value is 0, and 0 times a number doesn't change the number. The x-intercept stays the same. This is because the y value at the x-intercept is 0, and multiplying a number by 0, which is exactly what you're doing, doesn't change its value. And that's the reason for what it is. Okay, guys, I forewarned this section might not be for everybody. I honestly, it's really tough to state that it's even for IM1 in this way, although, again, I fully acknowledge why it's in the book how it is. So you entered this domain trying to understand some stuff, and I spent 40 minutes trying to get into those things. Now we're going to dive into the problem set. Based on what we're seeing here, it looks like, and I don't know if we're going to have to do a lot of graphs, but it looks like we're going to have to do a lot of descriptions, which means I'm going to have to do a lot of typing for this stuff. So get ready to do a lot of writing on your own as well. Maybe you can find nice, easier Cliff Note ways to do this, because I'm going to probably find ways to copy paste what I got to say. But guys, I'm going to go ahead and now finally get started. In exercises 5 through 10, use the graphs of f and g to describe the transformation from the graph of f to the graph of g. So it doesn't sound like we're actually graphing on these ones here, but we have visuals for 5 and 6. On number 5, we have f of x equals negative 2x. Now that's not the parent function, but it is just the original function we have. G of x is f of x plus 2. It takes whatever this was, negative 2x, and plus 2. The other one was negative 2x plus 0, right? So all I'm going to state here is the graph of g, and this is how I'm going to start most of what I state. I'm going to say the graph of whatever, the graph of g, the graph of h is a, and then we're going to state what it is. When there's a plus 2 right there, that's like a plus k, we're affecting our y values by adding 2 to them. So the graph of g is a, and I'm just going to copy that and get that ready. Whoa, what happened? The graph of g is a vertical translation. Sorry, is a translation 2 units up. If I say the word up, then we know that that means vertical in that case. From f. So g of x, I can just call g, f of x, because they're both functions of x. The graph of g is a translation 2 units up from f. And you can tell that that's exactly what's happening. Before we had a point right here, and now it's a point right there. And those are the ones that we can make sense of most, because this is the y-intercept of y equals negative 2x plus 0, and this is y equals negative 2x plus 2. And by the way, I'm glad that I'm doing this right here because the book didn't do that in the lecture portion. So negative 2x plus 2, it went 2 units up from negative 2x plus 0. Number 6, g of x equals f of, and inside the function is x plus 4. And then inside, in this one, here's f of x equals x minus 3. So here's the original function. Now we're going to use f of x plus 4. That means that x plus 4 is going to take x's place in the equation. So it'll be x plus 4 minus 3. Kind of weird. But what's really weird is whenever you're doing something inside the function, you have to do opposite. If this has a plus 4, first of all, it means horizontal changes, but it means we're not going to go right 4, we're actually going to go left 4. And you can tell that this looks like it is going to the left 4. And they're using the graph so that you can confirm it, right? I can confirm with this graph that all these points went left 4 from where they were before. So number 6, the graph of g. The graph of g is a translation 4 units left from f. So in that case there, again, keep in mind, anything that's done inside of the function is you have to do opposite of. I explained why in the 40-minute lecture portion slightly, but we're going to have to go with it. Number 7 through 10 does not have graphs. So at this point, we're going to have to just make sense of what it is, how it is. F of x equals 1/3 x plus 3. And g of x equals f of x minus 3. I don't know if you've noticed from the previous ones, and actually, you know what, I'm going to go back to number 6 in just a moment here just to explain it. But I don't know if you've noticed in the previous ones here, but I don't care what the original function is. I just care how it's being affected. We take the original function and we do this to it is what it's saying. That's all. Case in point, but however, this is where these graphs do help us because we can confirm we were doing it right. Look at the f of x plus 4 there. Remember, g of x takes the f of x, which was originally x, and it turns it into x plus 4, and now it's minus 3, and that becomes x plus 1, and that y-intercept is 1, and it has a slope of up 1 over 1. So if anything, I can confirm that my answer is right by seeing that's the exact graph that I expected it to be, but I'm not required to do that. Therefore, it officially doesn't matter what this function is. You can say that this is a vertical shrink by a factor of 1/3. You can say this is a translation 3 units up, but we don't care. We only care what the graph of g is compared to this one here. And I should have been copying and pasting these actual equations, so writing them down just like I did here. So I'm going to keep doing that. The graph of g is a vertical translation, it's a translation 3 units down. It's a minus 3 there, which is affecting our y values. Therefore, we go 3 units down from what they were before. So this is where I'm going to start to do more speed up of these, especially as they become more commonplace as to what we're doing. Number 8 as well does not have a graph. None of these things will, but we got f of x equals negative 3x plus 4 is, who cares what it is, right? Because we're going to take whatever that graph is and we're going to do a plus 1 to it. Plus 1 to it. And so the graph of g here is a translation 1 unit up. That's what the plus 1's doing to that f of x. We add 1 to this function. It becomes negative 3x plus 5 instead of negative 3x plus 4, which means the y-intercept starts at 5 instead of 4, and you do the exact same thing to the graph as you would have before. Number 9, we got f of x equals negative x minus 2, and g of x equals f of x plus 5. So the x plus 5 is inside the function, right? The plus 5 is inside the function. That means it's a horizontal translation. We do opposite of what it says. We're going to go 5 units left instead of 5 units right. Translation 5 units left from f. And then number 10, we have f of x equals 1/2 x minus 5, and g of x equals f of, and inside the parentheses, x minus 3. Now, I'll start typing out what this thing is while I state. My finger's already on the pulse when it comes to this, guys. I'm already 46 minutes into this video. I'm only into problem number 10 of 67. I feel like what I'm writing is not adding to whatever's over there because I'm not doing anything to them. So unless I do something to them, I'm probably not going to copy those down anymore. I hope that's okay. The graph of g, this is a translation 3 units right. Again, it's inside the function from f. This is inside the function. You do opposite of what that says. The x minus h, our translation is h units, right or left based off that. Okay, number 11, you and a friend start biking from the same location. Your distance d in miles after t minutes is given by the function d of t, okay, I guess I'm going to write this one, equals 1/5 t, just so we can see the information. Your friend starts biking 5 minutes after you. Your friend's distance f is given by the function f of t is d of t minus 5. Describe the transformation from the graph of d to the graph of f. Well, it takes your exact d of t function, what it is, but it's going to subtract 5 minutes from the t value, make a change there. Therefore, the graph of f is a translation 5 units right from the graph of d. So this kind of makes sense as well, right? You know, when we say t minus 5, that you have to take, you know, for your friend to be the same distance away from a starting point as you were before, we need to advance 5 units forward because that's when your friends start bike riding. So if you start riding at time 0 and you're at mile 0, or whatever it was, your friend is going to be at mile 0 at time 5. That's why we need to subtract 5 of those numbers to get that same height. Number 12. The total cost C in dollars to cater an event with P people, I'm just going to go and box them this time, is given by this function here. The setup fee increases by $25, so the new total cost will be C of P plus 25 with this T of P. Describe the transformation. So again, they have some information around the problem. They even show the Corey's catering thing right there, and we can hopefully make sense. You know, the more that they make equations for us, the more I hope that we understand how we can make those equations for ourselves eventually. But here we can say the graph of T, capital T, is a translation 25 units up. You know what? We have units for these. When I said 5 units right, we know the units. This is 5 minutes right. 5 minutes more. 5 minutes more. This is translation of $25 more, or $25 up, I should say, up from the graph of C. So instead of a $50 setup fee, it'll be a $75 setup fee. It's still $18 per person though, because 50 plus 25, right? In exercises 13 to 16, use the graphs of f and h to describe the transformation from the graph to the graph of h. Graph of f to the graph of h. So these are kind of what we were doing from the previous ones. We're still not graphing ourselves. They have the graphs for us. And like I stated, I'll let the things stay as they are over there. But this time we're not talking translations. This time we're talking reflections. Now, the first one says f of x equals 2/3 x plus 4. Maybe you can confirm the graph does what it does. And this says h of x equals negative f of x. So the negative here takes this thing completely, flips it all around. It's changing the y values. You plug in some x, it takes the y, and it flips it over. So the graph of h is a reflection. I think they say in the x-axis. I like to say over, but they say in the x-axis from f, from the graph of f. Now, what that means, though, is here is the x-axis right here. That's your line of symmetry, your line of reflection. And your points are flipping over from here to here, or from here to here, whatever they were. They're flipping over. The y values are changing from some positive, some negative, or from some negative, some positive. And the x-intercept stays exactly as it was, because that's still 0. So now it's negative 2/3 x minus 4 instead of positive 2/3 x plus 4, right? That would be the idea. Number 14 is a different kind of reflection. This one is flipping over the y-axis. Maybe you can tell because the y-intercept stays the same. And maybe we can also tell because, well, you know, they say f of negative x. And f of negative x means we're affecting something horizontally. See, this had a vertical affecting thing, even though we flipped over the x-axis. This is going to affect your points horizontally. Whoops, we go from black to red. But now we are flipping over the y-axis for that. So what's the graph of h? It's a reflection in the y-axis from f. Reflection in the y-axis from f. Numbers 15 and 16, I will not write the equations here because that has no effect on what it's going to do to our thing. That being said, this is not quite slope-intercept form. I wish it said negative x minus 5. Or not I wish it did, but if I were to rewrite it for myself and graph it, this is what I would do. But f of negative x here, once again, is a horizontal reflection. No matter what that graph was for f, the graph of h is a horizontal reflection, is a reflection in the y-axis from f. And then number 16 looks to take whatever your f of x equation was, and we're reflecting the x-axis. So these are very easy answers as far as what we're stating, but we have to get familiar with them so we understand it. Whenever something's outside your function, it affects y. If it affects y, that means for a reflection, it's flipping over the x-axis. Reflection in the x-axis from f. Okay. We're going to do the same things here. I need to copy and paste this one, or I'm going to change this to an R for a second and copy that. And then let's undo that. There we go. Okay, now we're going from F to R in these scenarios, and now we are changing things with horizontal reflection, stretches and shrinks. Now, horizontal is more difficult for people to comprehend from vertical. If you were in a part of my 35 to 40 minute lecture, you heard me kind of emphasize that then, and I tried to explain what it was. So I'm going to state the answers kind of as they are. Whatever f of x was here that you can see in black, this thing now appears to be, and maybe this is the way that, oh, I'm sorry, this one actually is a vertical one right here. So there, I think they're going to combine vertical and horizontal. Okay, that actually makes me feel a little bit better. This 2 is outside of the function. That means it's a vertical change in this. You can tell that this red is taller than it was before, and it's literally changing things like your slope. It's doubling your slope. It's also doubling your y-intercept, though, right? It went from -1 to -2, but instead of 3 over 2, now your slope is 3. It's going up 3 over 1, up 3 over 1. This is clearly a vertical stretch. The graph of R is a vertical stretch from F by a factor of 2. Everything is twice as tall as it was before. That includes 0. 0 is twice as tall as it was before. Guess what that means? The x-intercept is still where it was before. It's still the value of x when y equals 0. 0 times 2 is still 2. From F. So if you have to write this each time, I'm sorry. I legit don't think a lot of teachers will be assigning too many problems out of this, if any at all. Number 18, f of x equals negative x. Here's that graph. And now suddenly 1/4 f of 1/4 x. Now that means that we're still using the negative x as the function, but now we're multiplying it by 1/4, which to us, the x by 1/4, which to us can mean something in the vertical realm, but because it's inside the function, we have to speak about it horizontally. You can tell that in the horizontal realm, this thing's stretched. It's stretched here, it stretched there. It stretched 4 times more than it did before. The graph of r is a horizontal stretch by a factor of 4. Remember, anything inside of the function not only affects something horizontally, but it also does opposite of what you see in there. When we see a 1/4 inside there, that means you go 4 times bigger on your x's. Number 19 has a function, and we're going to take that 1/2. So it's literally the same thing as you had on number 18, only on number 19 it's now by a factor of 2. But it is still a horizontal stretch because it's inside your function, and we do opposite of what it says inside there. So I'm going to copy and paste that. I'm not sticking around long on these ones when they have patterns like that. Number 21 is a lot like number 17, only instead of a, where is it? Only instead of a 2, it's a 3, right? Again, whatever the function is what it's going to be, and we're about to triple their heights. Their y values are about to go times 3 bigger. So this is where I don't have to type a lot. It's already typed. It's a vertical stretch by a factor of 3 from f. I don't have an answer key in front of me, but go find the back of the book, and I don't know if they give the odds or whatever. Go to the back of the book. It's literally going to say things like this over and over. It's not going to be this is, I'm not saying it's not math, but this is not so much what you think it is. This one is going to take whatever the graph, because we're not graphing it, right? It says use the graph, so we're not graphing these. So I'm just describing what I stated before. This is a stretch of 4. It's because it's 4 times that thing. So hopefully you're making sense of what it is that we're doing. I know it's a little redundant and such. And listen, I'm speaking honestly about this stuff. This isn't the thing as a teacher that I like to really talk about or do. I'm doing the solution guide. I don't like doing this one. I'm going to give you my opinion on it. That's not saying it doesn't have its purpose. I'm just stating that from where you stand, understand that you're doing what's good to practice for IM2 stuff and things like that. And making sense of what's actually affecting graphs. Wait a second. Did I skip a problem? I'm sorry. I skipped number 20. How did I do that? I skipped number 20. So let's do this. Let's shift this down. Let's shift this down. This will be 22. Number 20 can change the 2. Maybe I don't know what I did. So this will be a horizontal stretch by a factor of 3. You know what I wish that they did here? Oh, you know what? They'll probably do it next. Never mind. Never mind. Okay. I think that's correct now. Okay. Numbers 23 to 28, same thing. We're going to go back to the letter H, though, instead of R. So I'm going to get this one prepped up and ready to go. So H. And let's go ahead and get ready. These ones look like they will be shrinks instead of stretches. So in number 23, you can see this is inside the function, this 3x from the original function as it is. And you can see that these things so we're horizontally affecting it. How so? Things are shrinking. They become 3 times smaller in the x direction than they were before. So therefore, the graph of h is a horizontal shrink. I'll also use the word compression. So every so often, I'm going to kind of change it. Horizontal shrink by a factor of, you don't say 3 this time, you say 1/3. You want to say a number that's between 0 and 1, so you're doubly emphasizing the fact that it is a shrink and not a stretch. If you say shrink by a factor of 3, I'm kind of okay with it, because that's like saying divided by 3 to me. But we want it to complement what it is that we were stating before with the shrink. Now, number 24, in this case, this is outside the function. That means you take your y values and you take 1/3 of them. Therefore, we're vertically affecting them, and they are shrinking. The graph of h is a vertical shrink by a factor of 3. Oh, 1/3 from f. I should be saying, if I don't say from f each time, I apologize. I'm going to try to. Number 25, you take whatever function it is, and this times 1/6. So it's going to be the same thing as number 24, only instead of 1/3, it will be 1/6. You divide your y values by 6. Like so. And you know what I'm going to do? I'm going to change the word this time to compression. Just because I use that word in other kinds of videos, especially in IM2, I use it more than I do shrink. I want to make sure that you know that. Maybe I should just type this one out just to have another one locked and loaded. So number 26, f of 2x, that one again is inside your function. 2 is more than 1 inside your function, that means we're going to shrink it horizontally. Compression. No. Your x's need to be half the size they would normally be because we're about to double them. That's what the 2 is doing there. It's about to double them. Now 27 is like 26, only now it's 5. Again, whatever the function is. That 5 means we now need to make our x's 1/5 the size of what they were. So graph of, or by factor of 1/5, it's still a compression or a shrink, either way. And number 28 is back to verticality because it's outside your function. We're about to make them 3/4 the size. 3/4 is less than 1. What was I writing? 3/4 is less than 1. Therefore, it's still a shrink. You still say the number of 3/4 from F. This time I use the word shrink again. Okay, in 29 to 34. Use the graphs of f and g, so they don't literally have graphs, but just the equations, to describe the transformation from the graph of f to the graph of g. This looks like more of the same, only now we're combining everything we did before, and now they are g's, so I'll get those ones ready. So nothing different from before, just mixing and matching different sets of them. Let's see if we now know them from what they are. Number 29. This one is what we just came off of. This one is a vertical shrink by a factor of 1/4 because it's multiplied outside of your function. So it's affecting the y's. They're 4 times smaller than they would be before. Number 30. You see, if I wrote all these equations down, guys, I'd be here all day. I hope that you're okay. Listen, I generally write things down when I'm affecting what I'm going to do with it. Here I'm just describing what's there, and I'm not actually having an affection to it. This one is going to be a reflection. It's actually a vertical reflection, therefore it's a reflection in the x-axis. The x-axis is a horizontal line, yes, but now it flips over that line vertically from F. So it's just flipping it over. I think we're about to do combinations of transformations later, so we might do a reflection followed by some other things that happen, but that's just the reflection. Number 31 is happening inside your function, therefore it's not only a horizontal change, but we do opposite of what it would be. Because it's a -2, you want to think, first of all, translation, and we're going to the right instead of to the left in that scenario, going to the right in that case. So a horizontal translation 2 units right. Number 32 is also inside the function, but this time because it's multiplying by something, it's a stretch or shrink. Because 2/3 is less than 1, keep in mind, you have to do opposite of that. You're going to have to stretch it, and by its reciprocal. So it's good we get one of these in. The graph of g is a horizontal stretch by a factor of, not 2/3, that would be smaller, 3/2 from F. Number 33, we have 6 times f of x. We're going back to the vertical stretch or shrink. This time it's a vertical stretch by a factor of 6. And lastly, number 34, again, I don't really care what the function is unless we're graphing it. Number 34, we say the graph of g is that's a translation. Now, outside the function, you do what it does. If it's -3, the y's are 3 smaller than they would be before. 3 units down from F. Okay. Very little math going on. All right, 35 to 38, write a function g in terms of F so that the statement is true. It says the graph of g is a horizontal translation 2 units right to the graph, or of the graph of F. So if I want to go 2 units right, 2 units to the right, that's inside your function, and that's the x minus h scenario. So g of x will equal f of, inside the function, we'll go x minus 2, like that. Number 36, we're going to reflect in the y-axis. The y-axis is a vertical line. That means we reflect horizontally. So we're going to reflect y-axis. It's a horizontal reflection. That means that is inside your function. That takes your x's and changes their signs. It makes them negative. G of x is f of negative x. Number 37 is vertical stretch by a factor of 4. You're going to see me write this abbreviation a lot in the future, VSF. Vertical stretch by a factor of 4 means we take our y values and we make them 4 times larger than they would before. So take whatever f of x is and times 4. So it looks like that, 4 times f of x. And number 38 says horizontal shrink by a factor of 1/5. That is affected inside your function. It is a multiplication. So horizontal shrink, I'll put a C for compression. Horizontal compression by a factor of 1/5. Remember, we need to make our x's 5 times bigger than they, we need to make our x's a fifth of what they are before. So therefore, we need to grow them 5 times larger to get the same y values as we would before. So f of 5x goes inside there. Opposite of what you see there. Flip it over. All right, in 39 and 40, describe and correct the error in graphing G. They show an f of x minus 2 from this f of x equals x minus 3. It seems like, therefore, we kind of need to graph these ones. I'll probably copy and paste the graph that you see there, though. Actually, no, I'll probably redraw them. So in this one here, now listen, they don't show you what the original functions are, though you could probably come up with them. When you see the minus 2, you might think go 2 to the left, and that's exactly what they did, and that's the problem. We don't go 2 to the left. We actually need to go 2 to the right. Remember, you do opposite of what's inside of there. So in correcting that error, we should be translating to the right, not to the left. So f of x minus 2, excuse me, f of x minus 2 means a translation 2 units right, not 2 units left. Now our correction needs to be in a graph. So I am going to graph this one. Come on, hit the copy button. I did. Register that it copied. Hit the paste button. There we go. Third time's the charm, right? Okay, the original function, now I don't know if you can tell. Oh, they did give you the original function. It's f of x equals x minus 3. Okay, let's practice that. That's a y-intercept of negative 3 and a slope of 1. So up 1 over 1 like this. Now, I'll show you this in terms of the translation, and then I'm going to confirm that the equation is what it was supposed to be. I think that's the best thing I can do for you in this section right now. Utilize questions like this. And I'm fine with questions like this. I'm just glad there aren't 67 of them that I have to do 2 graphs of. So here's our original function like this, right? Now let's take this. I'm going to copy and paste. No. I'm going to copy and paste this. I'm going to change its color up, turn it green or something, and let's translate it instead 2 units right. That means from whatever point, like the y-intercept here, or how about x-intercept? Let's go 1, 2 units to the right like that. This is what this new graph should look like ultimately, okay? Now let's confirm that we did this correctly by doing this. Take a look at the original f of x equals x minus 3, and g of x equals f of x minus 2. That means x minus 2 will take x's place in this equation to say g of x equals, instead of x minus 3, it's x minus 2 minus 3. And negative 2 minus 3 is negative 5. So x minus 5 is the g of x equation. Is this the g of x equation? Does it have a y-intercept of negative 5? Yes. And a slope of 1? Yes. So therefore, we have the correct graph now. What would have been before, with this one, we don't have a y-intercept of negative 1. Negative 2 minus 3 is not negative 1. So there's our fix. Number 40, they say, well, they don't say anything. Oh, they just drew a graph. So on number 40, they sketch a graph. We have negative x plus 3 as the original graph, and they put the f of x, or f of negative x for the graph of g of x. F of negative x should be affecting things horizontally. That means we should reflect this way. It looks like they reflected this way over the x-axis. We have to take a reflection in the y-axis. So f of negative x means a reflection in the y-axis, not a reflection in the x-axis. So once again, we're going to take another graph here, graph set. Let's sketch the graph of the original. I'll do a flip over of it, but I'm going to flip it over the other way. Well, it's going to look the same to you, only I'm going to move it in the right spot afterward. So let's do negative x plus 3. That is a y-intercept of 3 and down 1 over 1 like so. Actually, I'm going to do this. I'm going to stop right here. That way I go the same amount up and down. I go down 7, I go up 7. That way when I flip it over, it'll show as a true reflection, hopefully. But it needs to be symmetrical, otherwise it won't work. So in black, and this does have arrows, hopefully you can tell. Okay, I'm just going to have that one here. When I copy and paste this, I'm going to lay it right above this one in green. But we're going to take it and flip it over. So get ready in 3, 2, 1. Boom. And when I reflected that, that's a reflection in the y-axis. The y-axis is this line right here. Hold on, I'm working on it. It's this line right here. That's the one that we reflect over. We don't reflect over the x-axis, but that would be the fix. Now let's double check that. Let's take a look at the original f of x equals negative x plus 3. Our g of x equation is f of negative x. Therefore, we need to substitute negative x in for x in this equation. Now you notice there's already a negative there. That doesn't matter. We're going to substitute negative x in for x, which means it'll be the opposite of negative x plus 3. Opposite of negative x is positive x, so it becomes x plus 3. Is our equation y equals x plus 3? Y-intercept is 3, and we go up 1 over 1. Yes, it is. So that matches. Okay, numbers 41 to 46, they say graph F and H. Okay, so what I just did for my graphs before, I have to keep doing for these ones. So I was happy I wasn't doing graphs. Now suddenly, got to do some graphs. And I feel like we should. I feel like we should. It says graph F and H, and then it says describe the transformations. Now, you can describe them with or without the graph, and you can graph with or without the transformations, right? It's an either-or proposition. If you try and use the graphs to describe the transformations, I think it'll be kind of tough because it's a combination of transformations. So I think we just practice doing our graphs. Oh, you know what? The f of x equals x is the same each time for the first 4 questions. So what I'm going to do even more so with this graph is I'm going to have this locked and loaded ready for each problem we do. Remember, f of x equals x is the original parent function for linear equations. There's no real change on this thing. It's a y-intercept of 0 and a slope of 1. There's no change in y-intercept. The slope is very basic and normal. You don't see a number in front of there. And, you know, when you take IM2 and IM3, you're going to learn more about other parent functions for quadratics, square roots, logarithms, all this kind of stuff. They'll all look very basic. Whoopsie. They'll all look very basic. F of x equals x squared. F of x equals x cubed. Square root of x. Those are all the very basic parent functions pre-transformation of any of those graphs. So here's the original parent function here. I'm going to keep this for problems 41 to 44. Over to the side. You won't see it. Okay, and let's do another graph. So on number 41, I need to graph 1/3 x plus 1. So 1/3 x plus 1 is a y-intercept of 1 and a slope of 1/3. That's up 1 over 3, like so. But technically what you would have to do is you'd have to take that black graph. You'd have to first, oh shoot, what did I just do? You'd have to first multiply it by 1/3. Technically, if you want to get the graph that you have here, you would first have to have a graph that actually looks like this in green. Take your original graph, multiply by 1/3, so every point becomes a third of what it was from black to green. And then you translate it 1 unit up. That's how this description is going to work here. Okay, I'm generally not going to do that one in green, but I wanted to make sure to emphasize that one. So the graph of H is a vertical shrink by a factor of 1/3. That's in green. Followed by a translation 1 unit up from F. So it first needs to shrink and then it needs to translate. If I translated first and then shrunk it, well, then the y-intercept would be at 1/3 instead of 1. That's not what we want. So we have to describe these left to right, basically, if it's in slope-intercept form, if it's based off the function. Number 42. On number 42, we'll take the original f of x function that we had before. I'm copying and pasting it. No. My thing is not registering this copy and paste very fast. I hit the copy button. I pause like 2 seconds before I hit paste, and it still recalls the old history. F of x equals x, and h of x, this time equals 4x minus 2. Now, we still have to graph the 4x minus 2, and this looks like no real change from before. There's a vertical stretch / compression change, and there is a vertical translation. We're going to go up 4 over 1 this time. This is what we practiced in section 3.5 on y equals mx plus b. So I'm not spending a lot of time talking about the graph portion. We're describing the transformations. So you take your graph, f of x, and first thing you got to do is do the stretch. Make everything 4 times taller than it was. So the x-intercept stays at, the x-intercept stays at 0. And then we translate it 2 units down. So the graph of h is first a vertical stretch by a factor of 4 from f, followed by a translation 2 units down. And that's what's going on. Da, 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 da. That's all we have to do, right? Let me get this ready here already. And another one because I'm on a new page. Okay. Number 43. Same original parent function. Brand new h of x. All of these, hey guys, if you look at all the, I didn't notice this. All of these look like vertical changes, vertical stretches and shrinks, vertical translations up and down, right? So same-ish stuff from before. I don't need to state much more. I just need to do the graph and do the answer. So h of x is negative 3x minus 4. Ooh, there's one more thing that's affected here, right? What else is happening? Well, you'll know when we graph it. But the slope is negative 3, so we get to go down 3, right 1 like this, and up 3, left 1, and that's where they cross. Fun. But that means we have to describe one more thing with this. We do not say, listen, there's a vertical stretch, but we don't say vertical stretch by a factor of negative 3. What we have to do instead is we have to state that there's a reflection and a vertical stretch and such. And I think I really have to shrink the font these days here. The graph of h is a reflection in the x-axis followed by a vertical stretch by a factor of 3 from f and a translation 4 units down. Somewhere I think you have to say from f. I don't know where the best way is to say it, but that's what I put there. Number 44. So listen, what I'm doing, in all honesty, and I think I stated this when I started this problem set, is the graphs that I'm doing, I'm playing a little bit separately from what I'm describing. Meaning, I'm using my equations to make my graph. I'm using my equations to describe the appearance. I'm not necessarily using my graph to describe the changes because that can be a little more difficult. If we're required to do it for future problems, we'll give it a shot. But for now, let's make the graph and practice that. Start at 3 and we go down 1 over 2. And I think that's part of why I don't want to do it here is because you might think, wait, Mr. Robinson, didn't you translate up 3 first before you multiplied by negative 1/2? No, I didn't. I started up 3 because I know every point that I have is in relation to that 3 that I'm at. I'm well aware of that. So I'm adding 3 on my own without knowledge of anything, right? Because if I multiply by negative 1/2 from this graph, I'd be right here. But everything goes 3 units up. Not just this point. Everything goes 3 units up. I just start from that point. But we do first do the reflection and the vertical compression. The graph of h is once again a reflection in the x-axis, or a relfection from f, and a vertical compression by a factor of 1/2, followed by a translation 3 units up. So there's that. Now the next two have brand new, and this is where we got to be very careful. They have brand new f of x values. They are not the parent function. So what we do to affect this thing, this is where we have to either pay more attention to the graph or pay more attention to the equation. I will probably do it in equation form in terms of paying more attention to it and see what we can do off of that. So let's see, how do I do this? Because I don't have the original graph thing right here. I need to ungroup this. There we go. Oh, interesting. Okay, let's just move this off to the side. Let's get this out of the way. There we go. Okay. I have to graph this new f of x equals 2x. That is a slope of 2. It still has a y-intercept of 0, but it's up 2 over 1 instead right here. So the description in the change will be a little bit different. Just because you see a 6 in front of that h don't necessarily mean that that is a vertical stretch by a factor of 6, because you're doing it from this graph here, right? Now, we're not seeing this as h of x equals 6 times f of x. It literally says 6x minus 5. So let's graph it first, and then we'll see if we can make sense of what we have. What I think we can agree on is there's a translation 5 units down if you want to play it that way, and I think we should. Now, that's all I can truly fit. I'll fit this down 6 and over 1 like that. I'll try. And then I'll draw the line. Okay, but we have to describe this thing. Now, in order to describe it best, we have to see how it compares to the f of x here. You see, the f of x originally was 2x. That means I'm multiplying something by 2x here. H of x equals what times 2x? And then the minus 5, right? That's what's happening. Well, that's a 3. 3 times 2x minus 5. See, we've been seeing the equations before like this. 3 times f of x minus 5. And now we find ourselves trickling up into that scenario. But this is the one, or this one here. This is the one that's seeing the true change from the 6 to a 3. This was a 2x. It got tripled. Then 5 subtracted from it. So the graph of h, is a vertical stretch, but not by a factor of 6, by a factor of 3. Followed by a translation 5 units down. That was a little bit trickier, and that one's a little more useful in terms of looking at what we have there. Number 46, f of x equals 3x. And h of x equals negative 3x minus 7. No. I hit, oh, I have to unlock it first. Copy. No. Guys, I hit Control C. 1, 2, 3, 4, 5. There it is. Okay. It still takes an original copy of something. It's really, I don't know why it's going so slowly there. I apologize. F of x is this guy right here, 3x. H of x is negative 3x minus 7. So we're not vertically stretching anything this time, guys. It's already at a stretch point from the original parent function. So we're not stretching. We are changing something vertically, though. Well, actually, two things. But in terms of multiplication, there's a negative 1 applied. That doesn't make it a stretch. It makes it a reflection. So I think we can tell what's going on here, right? H of x takes the f of x that's there, makes the 3x negative, and then we're subtracting 7 from it. That means there is a reflection in the x-axis. Followed by a translation 7 units down. Oh, I have to still graph it. But here, let's try and do the graph this way this time. Let's do, because they're the same stretch factor, I'm going to take this graph here. I'm going to turn it green. I'm going to flip it over. There's a reflection in the x-axis, and let's go down 1, 2, 3, 4, 5, 6, 7. There's your graph right there. I know the window range is kind of stupid, and I can extend it, but I'm just stating that that's the appearance of the graph that we have. So we can keep going with that slope of up 3, left 1, like that. And then we can do it. But you can see why you have to kind of do the reflection first. If I translated 7 units down first, and then I flipped it over, then I'd actually have a y-intercept of positive 7, not negative 7. That'd be kind of weird. And yes, this does have a y-intercept of negative 7. Okay, let's move forward. Number 47, modeling with mathematics. The function t of x equals negative 4x plus 72 represents the temperature from 5 p.m. to 11 p.m., where x is the number of hours after 5 p.m. So it looks like every hour after 5 p.m., we're losing 4 degrees Fahrenheit in temperature. The function d of x equals 4x plus 72 represents the temperature from 10 a.m. to 4 p.m., where x is the number of hours after 10 a.m. So it sounds like from 10 a.m. onward, every hour we increase 4 degrees in temperature. Describe the transformation of the graph of t to the graph of d. Well, t of x is negative 4x plus 72, and d of x equals positive 4x plus 72. This one's a little tricky. This one's a little tricky because from t of x to d of x, from t to d, from t to d, you're not just reflecting because the plus 72 applies to both of them. Well, I take it back. You can reflect. You're just not reflecting in the y-axis. If you said t of x is negative d of x, that wouldn't work because that would be positive 4x minus 72. You would have to change both signs of both things. But what you could do instead of a vertical reflection is a horizontal reflection. If you want to turn 4x into negative 4x, you could treat this as being inside the function like this. Negative 4x to positive 4x. You can treat it as inside the function here. That means you can say that your t of x is the opposite, or d of the opposite of x. So what you're actually doing is you're not multiplying this by negative 1. You're multiplying this by negative x. Multiplying it by negative x, and it's changing there. I think I'm saying that right. The negative x is multiplying by 4 instead of negative 4 being multiplied by x, or negative 1 being multiplied by x. Okay, so anyway, describe that transformation. It's a reflection in the y-axis. The graph of t is a reflection in the y-axis. That doesn't change the 72. Oh, the graph of d. Or from t. Okay. Number 48. A school sells t-shirts to promote school spirit. The school's profit is given by the function p of x equals 8x minus 150, where x is the number of t-shirts sold. So they're talking about profit, which makes it sound like $150 was spent on basically making the t-shirts, and now you have to start making profit from there. $8 per shirt sold. During the playoffs, the school increases the price of the t-shirts. The school's profit during the playoffs is given by the function q of x equals 16x minus 200, where x is the number of t-shirts sold. Describe the transformations, plural, from the graph of p to the graph of q. Second of all, so I'm going to write the equations, but the next one sounds like there was higher cost. Maybe it was for what they had to do by having them be special, or maybe it's just because they made more of them. But the cost is more on the playoff ones than it is on these, but they're also selling them for more. But we're just talking about transformations, right? So we have to somehow go from 8x to 16x. We somehow have to go from negative 150 to negative 200. Now this might have to go one at a time, right? So q of x, let's say we just said that it was 2 times p of x. We doubled it because that way we'd be doubling the 8x. The problem is you're also doubling the 150. Now, we can work on that because that's 16x minus 300. But we need to change the negative 300 now to a negative 200. So why don't we add 100 to this as well? Because negative 300 plus 100 is negative 200. So this is an option that we can do. We can say that we vertically stretch things by a factor of 2. We're basically doubling our price, which to us might seem like we're doubling our well, I don't know what it seems like. I'm trying to give real world context as to why something would actually now be minus 300 in the case of doubling our price. But we're I guess to say to sell the same amount of t-shirts, we could spend twice as much money. We're doubling our price, but we could now spend twice as much money if we'd like to sell the same number of t-shirts. But we don't want to do that, and we want to spend not twice as much money, so we want to spend just $100 less by adding 100 to our overall profit. We want to make $100 more profit than that. Okay, we'll add 100 to the profit. So there's the idea. So how do we describe that? The graph of Q. Well, I don't know if we say the graph of Q now. They just said describe the transformations. The transformations are a vertical stretch by a factor of 2 from P to Q, followed by a translation 100 units up, or $100 up if you want to say that. I didn't really say that for the last one. There's more than one way to do this though, right? We could have talked about a horizontal stretch or compression or whatever. I'm not as big a fan of horizontal things unless I feel like I have to do it. This one felt a lot better to do a horizontal one, a reflection in the y-axis. Okay, number 49. The graph of g of x equals a times f of x minus b plus c is a transformation of the graph of the linear function f. Select the word or value that makes each statement true. All right, I'm probably going to copy and paste those sentences, and then I'm going to write in those words that fit them. Note, I do not know whether the words can actually fit. If they're like, hey, we made this one bigger because it's a bigger word, I have no idea. So let's go and give it a shot, see what's going on. So first of all, the equation thing we have is g of x equals a, which sounds like a vertical stretch, compression, or reflection in the x-axis. X minus b, which can be a translation left or right, depending on what we have there, and plus c, a vertical translation up or down. The graph of g is a vertical blank of the graph of f when a is 4, b is 0, and c is 0. Remember, if b and c are 0, that means they're just not here. They're not affecting. So it's more like a times f of x, and the a value is 4. So this looks like g of x equals 4 times f of x. Well, that is a vertical stretch. Vertical stretch, and that's the word stretch we're saying right there. We're not indicating what factor it is. We're just stating that it's a stretch. Part B, the graph of g is a horizontal translation when a is 1, b is 2, and c is 0. I want to remind you that a kind of can't be 0, because if a is 0, then this whole thing wipes out, and we don't want that. So when a is 1, then the a goes away, because 1 times the number is just the number. So when a is 1 and b is 2, this looks like an equation that says g of x equals f of x minus 2. Whatever the function is, there's the x minus 2 inside there instead of x, which means we translate 2 units. Is that what we're saying? Wait, hold on. What did we say? Oh, to the right. To the right. Horizontal translation right of the graph. Remember, it's opposite of what's inside there. And then part C, a vertical translation 1 unit up. A is 1. Again, no change there. B is 0. No change. C is added 1 unit up. So this is going to look like g of x equals f of x plus 1. And outside the function is vertical indeed, and we are going up. Oh, they did say up. Oh. 1 unit up is c equals 1. Got it. I kind of answered it without realizing I answered it. Yes, 1 unit up looks like the c value is going to be 1. So that was this one here, and this was right, and this was stretch, and those are the only answers that we had. Unless there are more parts on the next side. Nope. Oh, but there's a whole nother problem of this same form. So number 50. Slightly different structure. Let's write it out. H of x equals a times f of, this is bx minus c. Now this can get super confusing here. This honestly is not an IM1 question already. The way that this is written. Oh my gosh, they're doing this to you. Okay, I don't know what, okay, we'll see if they give you a b and c that's when b is not 1 and c is not 0 at the same time, and I'll see how I can explain it. Otherwise, I think we're going to be okay. I don't think they're going to put both together. That would be incredibly cruel, because you don't know that much about factorization yet, or the appearance of this form. Knock on wood. Actually, let's take a look right now. Is there ever a problem where b is not 1 and c is not 0 at the same time? No. Okay, thank goodness. Okay, I feel a lot better. Moving on. Here we go. The graph of h is a blank shrink of the graph of f when a is 1/3, b is 1, c is 0, d is 0. Remember, when b is 1, this goes away because 1 times something is that. C is 0, d is 0. Looks like a times f of x. And a is 1/3. This is h of x equals 1/3 times f of x. That means this is a vertical shrink. Oh, a vertical shrink. And I don't know if we use something more than 1, so I'm just going to cross it out. Didn't look like we did last time. I doubt we will this time. Part B, the new change here, b is -1, whereas everything else, it looks like everything else stays the same while we're doing something. So this time this is g of x equals, now when b is -1, -1 times x is -x. So f of -x, and they're talking about a reflection because it is 1 when we make something negative. It's a reflection in the y-axis. It's a horizontal reflection, and the y-axis is what is done on this guy here. Let's change the color though. So there's that guy. And then the third one, What changes now? It changes in the description. There's a horizontal stretch by a factor of 5. Now, given that, oh, hold on, y-axis, where is it? Given that it's horizontal, it's going to be inside the function, which means we have to do opposite of what's changing there. So this case, it's actually going to be g of x equals f of 1/5 times x. b is 1/5. That's one of our options here, and that's the one that we're trying to choose. Okay, number 51, analyzing graphs. Which of the graphs are related by only a translation? Explain. Are related by only a translation. So we're matching sets of graphs together. How many are there? 6. So we're going to match, I guess, 3 pairs, or maybe more. I don't know. But let's, we're finding ones that have the same slope. Now, there are, let's see, 51. Actually, maybe it's not 3 pairs. Maybe I don't know. Let's look. We want to find ones with the same slope. Are the scales the same? Yes, they all go by ones. Okay. This has a slope of 2. Hold on. I'm going to do something for a second here. This has a slope of 2. This has a slope of 1. This has a slope of 1. This has a slope of 1/3. This is a slope of -1. And this has a slope of 2. So graphs with the same slope are related by a translation. Ones that don't have the same slope will not match at all. D and E do not have any matches whatsoever. Slopes of 2, A and F, have the same slope of 2. B and C have the same slope of 1. Therefore, you can use translations to match those two graphs without needing to reflect or vertically or horizontally stretch or shrink. So, A and F are a pair, as well as B and C. Each pair has the same slope and therefore can match using only translations thereafter. Thereafter more. All right, number 52. Analyzing relationships. Was that this one too? No, analyzing graphs. Was this analyzing relationships? No, using structure. Okay. Doesn't matter. A swimming pool is filled with water by a hose at a rate of 1,020 gallons per hour. And they're going to give us the equation down below. The amount V in gallons of water in the pool after T hours is given by V of T. And V might stand for volume when they say the amount. Equals 1,020 T. How does the graph of V change in each situation? It says a larger hose is found, then the pool is filled at a rate of 1,360 gallons per hour. Well, I'm going to make a new one here. I'm going to call this L of T for a larger hose. A larger hose being 1,360 gallons per hour means it's going to look like this. So this is part A. Does that mean that's a translation? No, in fact, it's a vertical stretch by some kind. I need to multiply 1,020 by some value to get 1,360. What is that number? Even I don't know, but I can use a calculator for it. And here I'm going to be doing 1,360 divided by 1,020 to figure it out. That's how it's going to change it. So when I go to my calculator and I type 1,360 divided by 1,020, it gets a crazy number of 1.3 repeating. Now 1.3 repeating as a fraction, for those who are aware, is 4/3. Whoops, not cubed, hold on. Is 4/3. So 4/3 is the vertical stretch of this thing. So instead of being 1,020 gallons per hour, it's now 1,360 gallons per hour. So this is a 4/3 that goes here. And that's the change on this thing, right? It's 4/3 times V of T. So we are vertically stretching this thing by a factor of 4/3, and that's the change. You could also say it's a horizontal shrink by a factor of 3/4. I prefer the vertical stretch personally. So the graph of L, which I'm calling that, of L, is a vertical stretch by a factor of 4/3 from V. Part B says before filling up the pool with a hose, a water truck adds 2,000 gallons of water to the pool. They say before as in it's unrelated to the time. that's done here in hours. So let's see, a water truck, I'll call W. W of T, it takes your V of T equation, 1020 T, but we're also, regardless of T, filling up 2,000 gallons to it. This is unrelated, again, to the V of T because it's not affected, because it's not affected by T itself. It's not affected by time. When time is 0, you still have the 2,000 added to it, whether it's before or after. But the graph here is a vertical translation. It's 2,000 units up. So the graph of W is a translation 2 units up from V. I think they're all from V, right? They're not from like the part A or whatever. Okay. Number 53. You have $50 to spend on fabric for a blanket. The amount M in dollars of money you have after buying Y yards of fabric is given by the function here. So it looks like you probably start with $50 and you spend $9.98 for every yard of fabric. How does the graph of M change in each... Oh, here it is, $9.98 per yard. How does the graph of M change in each situation? So we first start with M of Y. Interesting that Y is now our independent variable, but that's exactly what it is. It's for yards. So that makes sense. What was M? Money? Yeah, M, money. You receive an additional $10 to spend on the fabric. That means, you know, we had $50 to start off with, right? Now we kind of have that 60. So receive, part A, I receive whatever I have here to spend plus an additional 10, right? That's kind of what's happening. That's what makes this turn into 60. So my description for that is the graph of R is a translation 10 units up from M. It'll take 10 more dollars to, you know, we can probably at least buy 1 more yard of fabric, right? That makes sense. Part B, the fabric goes on sale and each yard now costs $4.99. So M of Y equals, now it's $4.99. So I don't know if this is still, I think it's based on the original one. How does the graph of M change? Oh, not M of Y, I'm sorry. Let's call it sale. Let's say S of Y. S of Y equals, we are going to have it go on sale. Now, we do not just vertically compress this thing because we are now spending $4.99 times Y, but we still have the original $50. So we don't want to call this one a vertical compression. Otherwise, 50 would also divide by 2. That says, and oh, by the way, you have half the money to spend. We don't want to do that. We do want to change the $9.98, though, into $4.99. Sounds like you take half of it, but not the half of 50. So we need to do 1/2 times your $9.98, like that, which means that's going to be S of Y will take M of 1/2 of your Y here, then plus 50. So we want to make that 1/2. That is a horizontal change, but it's a horizontal stretch. It's a stretch, which means you can buy twice the amount of yards of fabric than you could have before. That's how we say it. So it's a horizontal stretch by a factor of 2. So the graph of S is a horizontal stretch by a factor of 2 from M. Once again, you don't want that to be vertical because we don't want to change our y-intercept. Is basically the way I'm going to say that. Okay, number 54. Thought-provoking. Write a function g whose graph passes through the point 4,2 and is a transformation of the graph of f of x equals x. So for this one here, you have to remember that with f of x equals x, this point goes through 0, 0. We need to come up with a g of x equals something that goes through 4, 2. To go through 4, 2, we want to translate 4 units right and 2 units up. 4 right, 2 up. So we want to take our f of x equation. Whoa, I don't want everything to move though. We want to take our f of x equation and we want to go 4 to the right. That means we want to go x minus 4 inside of here. 2 up means a plus 2 on the outside. So our new equation will now say g of x equals x minus 4 takes x's place. Then 2 gets added to our function like that. and negative 4 plus 2 is negative 2. G of x can be x minus 2. There is a version using only translations that'll get you there. There are multiple answers that you can do because, of course, you can hit that by translating up a certain amount, and then you can flip it over and vertically compress it, things like that. But this is using translations only, which will get you into that point. Oh, is a transformation? Okay, can I just use a single one? I hope I can just use a single transformation. Okay, anyway. Now listen, here's another one I could have done. In a single transformation, I get, you know what, technically this is a single transformation. 4 right and 2 up also just means 2 down. According to this graph, 2 down. Another one I could have done over 4 up 2 also means up 2 over 4. And up 2 over 4 means a slope of 1/2. So we could have vertically compressed this by a factor of 1/2, like this. So there's a slope. No change in y-intercept. You just go up 1 over 2 twice, and then boom, you hit it. There are a lot of ways you can do this one. Numbers 55 to 60. Graph f and g. Write g in terms of f. Describe the transformation from f to g. Okay. These are like what we did before, only now we aren't starting with that parent function quite as often anymore. We have to get more comfortable doing transformations from one to the other based on what's present. So on number 55, we have f of x equals 2x minus 5 and g of x equals 2x minus 8. It looks like a very simple transformation going from negative 5 to negative 8. Looks like it's a change of 3 units down, and when I say it looks like, I mean it is. That's right. I'm not tricking you. So that's the answer, but we still have to graph them, and we can confirm. No, I copied that so long ago. What is wrong with my software? Thank you. Okay, anyway. I hit that copy button about 4 seconds before I pasted. I intentionally gave time. Anyway, f of x I'm going to do in black. G of x I'm going to do in blue. So slope of 2 with the y-intercept of negative 5 like this. And you know what I think I'm going to do? I'm going to translate this 3 units down. Oh, let's see. How do I say this? I'm going to copy and paste my graph and translate it 3 units down. Instead of drawing the new graph, this one, if there's no stretches, it's really easy to do translations on. So I'm just going to take this, copy, paste, make a different color, and let's take that one and go 3 units down. It's easy to go from the y-intercept. 1, 2, 3 units down. Does that not make sense that it should be a negative 8 y-intercept there? It totally looks like it, right? So the graph of G is a translation 3 units down from F. That's it. There we go. Weird spacing, sorry. All right, number 56. Number 56 has what looks like a couple things going on with it, but if you play your cards right, you might be able to do this in one transformation. So f of x equals 4x plus 1. And these are ones where drawing the graph first could help you. If you also work out your transformations in such a way to understand what's going on, both signs changed. Both signs changed. So what we could think about with this one is g of x is just the opposite of f of x, right? It's the opposite of f of x because it's the opposite of 4x plus 1. G of x is the opposite of 4x plus 1. Therefore, it's the opposite of f of x, which means it's a reflection in the x-axis. And that's what we could do on our description for this next one. I have to copy this graph over. Let's see if this works. Control C. I pause, paste. Yes. Okay. So f of x equals 4x plus 1. I still have to graph. And let's see if we can just do a reflection in the x-axis. So positive 1 y-intercept and a slope of positive 4 over 1, like so. What's my line? It's this guy right here. Okay, I want to take this graph and I want to reflect it over the x-axis. In doing so, I should hopefully get the graph of my dreams, the graph that I've been so waiting for my entire life. So let's change the color. Let's place it in the same spot. And let's flip this guy over. Boom. Is this not, probably a little realignment, but is this not that graph? The slope is negative instead of positive. The y-intercept is negative 1 instead of positive 1. It seems to have reflected across this axis here. That's what we were looking for. So the graph of G is a reflection in the x-axis from f. That's in one step. Okay, number 57. F of x equals 3x plus 9. G of x equals 3x plus 15. I think we can easily say here that there's a translation 6 units up. I think y'all would agree. The problem is when it comes to graphing is I probably can't fit it the same way. So I'm going to have to kind of come up with means of doing that. But g of x takes your f of x and plus 6, right? 6 units more than it was before. There's my plus 6 like that. So let's do the f of x graph. And now how would you do this if you don't get that y-intercept? I hit copy. Come on, copy, paste. No, copy. No. Oh my goodness. Control C. Copy. Copy. No. No. Copy. 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 Don't crash my... Thank you. Guys, I don't know what's going on with this. I feel really bad that that's happening on these ones. I'm trying to copy and paste a graph. I really need it. Oh no, now something else got affected on my software. Guys, I'm going to pause this. Give me 1 second here. Okay, I restored what I had before. Okay. Yes, so let's graph the original 3x plus 9. Now, this might be one of the first graphs we do where not only can the second y-intercept not fit, but this one barely fits to the extent that if I want to try to go up 3 over 1, I couldn't fit it. Here's a common mistake people do. If they can't go up 3 over 1, they tend to go down 3 and right 1. They tend to make their graph negative just because they're like, oh, I still want to go to the right. No, you can't. You can't just change direction. If I go up and right, that means I should also go down and left. So we'll go down 3, left 1, and fit the rest of this graph. And that's fine. Down 3, left 1, like so. This is one of the graphs where, and I'm not going to copy and paste this one. I'm actually going to draw the next one. But this is the one where using this transformation will actually be very helpful for us. This is one where you could obviously use a table of values. Because here's the thing. You only need one value to start off, guys. You do not have to graph from your y-intercept. You can graph from whatever point you'd like. Now, you can also take, based on the transformation, the exact thing that's happening. Translate everything 6 units upward. You go up 6 units from where you were before on every point, such as this point right here. Let's go up 1, 2, 3, 4, 5, 6. This is part of your g of x graph. Now, I can either take this one and count up 6 and count up 6 and count up 6, or from this point, I can also go up 3 over 1, etc. And that should, in effect, do exactly what we wanted. Can I see 15 up here? No. Would have it hit it? Yeah, probably. And by probably, I mean yes. Yes, it would have. So this is that graph of g of x. It is drawn. It is drawn based off the translation 6 units up, which was very helpful. I could have also substituted any value for x. For example, if I substituted -5 for x, -5 times 3 is -15 plus 15 is 0, and then applied the same slope. So that does have a slope of 15, or a y-intercept of 15. You just can't really see it for what it is, and that's okay. Anyway, they look very parallel as well, as they should. The graph of g is a translation 6 units up from f. Okay, number 58. Oh, as I've been sitting here for a while. Number 58. F of x equals -x minus 4, and g of x equals x minus 4. Unlike number 56, the -4 here doesn't change. And what I'd like to do is do this in one step. This will be a little bit like that thermostat question, or whatever it was, the temperature outside, and the, well, mostly like that one. The only thing that's changing is x, right? So my g of x is really taking whatever f of x was. See, f of x looked like this originally, but instead of x, to make this thing positive, inside here would have to be negative. That means g of x is taking f of -x right here. The -4 was still a part of that original equation. This is the new substitution and change. If that's all that's happening, just that sign, not the other sign, this is a horizontal reflection over the y-axis. And that's what we're doing here. So let's copy and paste. Let's see if this actually happens here. Okay. Copy. You can trust I copied. Paste. Okay, good. Now, the original graph is -x minus 4. Oh, minus 4. So down 1, right 1 for negative slope. Now for this one, I will just graph the other one as it is, and let's see if it looks like a reflection in the y-axis. How about that? We'll say, does it look like one to you, you know? So there's this graph here. And now I have f of negative x, which means reflected over this axis right here. So x minus 4, because they gave us the equation, right? But did I describe it correctly by saying a reflection in the y-axis? I think so. When you look at this, the y-intercepts are the same, and that's what's expected. X-intercepts went opposite of, as well as every other x value that swapped sign. That's the idea. All dem signs have that swappage. And that's what we have. So the graph of G is a reflection in the y-axis from F. Okay. So there's number 58. 2 more on this set. And then we go to 67, right? So I think 7 more to go until, or, well, 9 more to go. 7 more after these 2. And maybe they're longer problems, maybe they're shorter. I don't know. This is going to be one of them longer videos, though. Long lecture. I apologize. Well, you know, this thing was what it was. Number 59. F of x equals x plus 2. And g of x equals 2/3 x plus 2. It's one of those things where, again, as much as you see a 2/3 in front of here, you don't want it to affect the 2 as well. It's not like it's a vertical shrink by a factor of 2/3 because only the x got affected. So we want to think of g of x as taking whatever f of x was, this x here, but we want to call that 2/3 x. The plus 2 on the outside was kind of still sitting there from the f of x. So g of x, instead of f of x plus 2, it's f of 2/3 of x plus 2. Now to us, we see a 2/3 inside there. We say, hey, cool, horizontal shrink by a factor of 2/3. No, it's horizontal, but it's a stretch. This is horizontal stretch by a factor of 2/3. 3/2. The graph of G is a horizontal stretch by a factor of 3/2. We need to keep the y-intercept the same. But the factor of 3/2 means every x value is 1.5 times bigger than it previously was. Let's see if this aligns, even just by graphing these exactly as we know how to, slope and y-intercept. I'm fine with that. We'll just see if that aligns in that way. So this has a slope of up 1/1, like so. Now, we might not see each individual point in that light because the way that we graph fraction slopes, I'm going to say up 2/3. So maybe there's some points we skip, right? But along the lines, you'll still see that it is a horizontal stretch. Is it a vertical compression of sorts? Sure, but we can't call vertical compression because the 2 is still a 2. We didn't shrink 2 to 2/3 down. It still starts at 2. But we go up 2/3, boom. This point is 1.5 times farther away than that point. We go up 2/3, boom. 6 away is 3/2, 1.5 times farther than 4 away. Up 2/3, boom, 9 is 3/2 farther than 6, like that. Down 2, left 3 does the same thing on this side in the negative x values like that. Now, one thing that, we're not doing the table stuff that the book was using. If we did the table stuff, guys, I'd be here for like 5 hours. Literally, I would. I'd be here for maybe even more. I'd be here for a really long time. We just learned how to graph out a slope-intercept form, so we sure as heck ain't doing any of that stuff there. But the tables were a great portion in the lecture of explaining how these are what they are, why it's a horizontal stretch, and how it affects our x values as a whole. Now we're using our graphs to confirm it, the way we know how to graph them. Number 60 is f of x equals x minus 1, g of x equals 3x minus 3. Looks like everything just gets tripled, right? The g of x here, looks like we get to triple the x and triple the 1. So tripling x minus 1 means we're tripling our f of x's. Tripling our f of x's sounds like a vertical stretch. That includes the negative 1. That got tripled as well. So that's the best way to describe this one. The graph of G is a vertical stretch by a factor of 3 from f. Everything's 3 times bigger. Every y value. Every y value. So negative 1 y-intercept with a slope of 1 for our original f of x. And now the G, every y value, and this is what you can see in tables, right? Once again, this is where the lecture portion would have really helped. You said, oh, the x value before, or excuse me, at this x value, the y value before was 3, now it's 9. The x value before was negative 1, now it's negative 3. And that's actually the one we get to see on the y-axis. But here's the original graph. And our g of x graph was, yeah, oh, the y at x equals 0, the y value is -1. Now it's -3, right? Y-intercept. We go up 3 over 1. It was 0. 0 times 3 is 0. Up 3 over 1. It was 1. Now it's 3. It was 2. Now it's 6. At this x value, it was 3. Now it's 9. And I can't fit, but it would be from 4 to 12. And you triple them. But of course, we can sketch this graph as we know how and let that still be what it was, as long as we can feel it out. So there's no one way to answer these questions, whether you use the graph or the equation to get them. I'd say the equation's easier, for sure, especially when there are translations involved, although this doesn't have one. The graph of G is a vertical stretch by a factor of 3 from F. Okay, 7 more questions to go. Let's see how they do go. Number 61, reasoning. The graph of f of x equals x plus 5 is a vertical translation 5 units up from the graph of f of x equals x. I agree. How can you obtain the graph there using a horizontal translation? Okay, so we kind of saw on, before I get to the problem, we kind of saw on number, this one, it was like an open-ended or something. This, we had to go through 4, 2. I said, let's go 4 right, 2 up. And boom, apparently that was the same thing as going 2 units down. And that's the weird thing about these graphs, right? Linear functions, you have the ability to do different forms of translations and still land on the same spot because it's just a line. This line goes forever. So I could duplicate that line. I can go up this, I can go up this much and left that much, or I can just go left that much and I still end up on the same line, right? They might not represent the same kinds of points we were talking about, but they still get there. So if I have f of x equals x, now they use the same f of x here. I wish they had g of x. But if they have f of x equals x and f of x equals x plus 5, that does mean that we're looking at these graphs right here. I think if you draw them, it'll make a lot more sense. And I'm going to draw them as quickly as I can, which means I'm literally going to go here. This is f of x equals x. And f of x equals x plus 5, y'all, is going to look like this, a slope of 1 and a y-intercept of 5, right? So how can I take this graph besides moving 5 up and still line this up? Remember, the domain's all real numbers. That means that these lines technically keep going in these directions, right? So this graph, I'm going to make them even bigger just to really hold down the fort and say that, hey guys, these actually would have kept going. So imagine they're just this big, this huge. We could have also gone 5 left. Could have also gone 5 left. So instead of translating 5 units up, you could also translate 5 units left. And you still end up in the same spot. You still get the same y-intercept as an answer. If you recall, 5 units left inside your function would show an x plus 5 in parentheses like that. And that still explains the same thing. You do the opposite of what it shows. All right, time to shrink that one up because it's going to get in the way of number 62. Actually, I might have to do it on the next page. Let's see. Number 62. Whoa, how do you see it? Match each function with its graph. Explain your reasoning. The original f of x equation is right here, okay? So the original f of x is right there. Now, I see A or B. B is a translation 2 units up from this one. So where I'm looking for a translation 2 units up, let's see. I'm not looking at my options yet, but 62. So for... Oh, unfortunately, they have equations. Okay, but anyway, for B, I'm looking for something 2 units up. So which one is a 2 units up one? Looks like it's option C. Okay, I'm kind of going opposite of what I should be doing here. Okay, let me do it again. Part A is A of x equals f of negative x. Okay, I'm looking for a horizontal reflection, a reflection in the y-axis. So which one's going to be a reflection in the y-axis? It looks like graph A. Take a look at this. Boop. Looks like it's going to be A right there. That's a horizontal reflection in the y-axis. Reflect y-axis. That's my reasoning. Part B. G of x equals f of x minus 4. To me, that looks like or sounds like a translation 4 units down of the original f of x graph. So, which one's that going to be? Looks like D. 1, 2, 3, 4. So that looks like D. Translate 4 down. Part C was the one that matched graph B, right? F of x plus 2. That's a translation 2 units up. So graph B is 1, 2, up like that. Now this part D must be graph C, which kind of glad they saved it for last because that's the hardest one to kind of come up with, and you have ways to figure it out, but it says f of 3x. For one, they went by horizontal compressions instead of vertical, things like that. But for another, yeah, it's not just a translation or a flip. So take a point like this, we horizontally shrink by a factor of 3, now it's 3 times closer than it was before, like that. Or take this point, horizontal compression 3 units closer to the y-axis is now right there. So these things shrunk by a factor of 1/3. So therefore, it's going to be that, or process of elimination. But k of x equals f of 3x. It's really, I mean, if you want to explain something else just by, not just process of elimination, but just multiple choice options or matching, it's the only one that's not a translation or reflection. It's the only one that's going to have a size change. Graph A, the blue one, isn't a size change. It flipped over, but it's a reorientation, but it's not a size change. But this is a horizontal compression by a factor of 1/3. Hardest to determine, but given the last answer and stuff, it's good. All right, 63 and 66, 63 to 66, they want you to find the value of r. So on 63, we have an f of x minus r based on f of x. You notice the x minus r is inside of here. They're not asking to explain, so I'm not going to write more out, but we have to translate it to we have to horizontally translate it. So take a point, figure out how many units it goes over. It looks like 2 to the right. Therefore, our r value is 2. So for the g of x equals x minus r, listen, it's all written over there, so I'm just going to go straight up, guys. R equals 2. 64, this time your r is multiplying by x inside the function instead of subtracting from it. That's a horizontal stretch or compression factor. Because this thing's going outward bigger, it's going to be a stretch, which means you have to flip the r from whatever it is. Keep that in mind. Take a point that you have on here that you know pretty well, like this. This is 1 away from the axis. Now it's 3 away from the axis. That's not adding 2. That's multiplying by 3. If you want to see another one, take a look at this one that's 2 away. This one's now 6 away. That's another times 3. So it's a horizontal stretch by a factor of 3. Therefore, r is 1/3. Remember, when it's inside the function, it's there. That's again. So this is translate 2, right? I will kind of explain it. And this is horizontal stretch by a factor of 3. Kind of opposite, kind of weird, but that's how it works. Number 65 is something with vertical change. These ones are kind of easier for us for the most part because it kind of treats it as slope. I'm not really looking at this function too much, by the way. I want to see how one value compares to another. This one becomes twice as large right here. This one becomes twice as large right here, and this one becomes twice as large right here. Looks like the vertical changes by a factor of 2. So that's going to be an r value of 2. Again, vertical stretch by a factor of 2. You keep it as it is, whereas this one flips inside horizontally. So did this one. This one changed because that was a minus. And number 66 is plus r outside of the function. That also means you keep the sign as it is, but this is a translation. We go from f down to here. That means r will be negative. And be very careful because I just noticed this as well. These scales go by 2s. 2, 4, 6, 8. So we're going from 8 to 0 or from 6 to negative 2. We're subtracting 8 each time here. So our r value this time is negative 8. We're adding negative 8. That means we're subtracting 8. We're going down 8. And our last question is number 67 on critical thinking. It says, when is the graph of f of x plus w the same as y of fx plus w for linear functions? Explain your reasoning. The only time I can think of, it might be for everything. Hold on. I was going to say the only time is when it's 0. But, we just saw this. Oh, you know what? We don't know what our function is. Hold on a second. Let me go back really quickly here. Remember this problem? Remember this problem? Just 8 minutes ago. On this problem here, notice this was f of x equals x. Specifically x. Okay? A slope of 1. So when I did my graph on this question number 61, going 5 left, it was the same as going 5 up because the slopes were 1. But if the slope was 2, going 5 left means I'd have to go 10 up. So those wouldn't be the same. So the plus W thing would have applied when the slope was 1. But in other cases, that might not be the case. So I have to think of how to get the best explanation out of it given f of x. But if I have y equals f of x plus w, which means translate w units up or down, depends on the sign of w, or not at all, and y equals f of x plus w, they are the same when, one case I can think of for sure, they are the same when either w equals 0, that means there's no change, no translation whatsoever, that means they're the exact same. If the slope for the linear function is 1, if the slope of the function is 1, because we just saw that on the previous one, the slope was 1, if I go this amount of units up and I go this amount of units left, I'll be the same thing. Or this amount of units down and this amount of units right, I'll be at the same place if the slope is 1. What I'm curious about is if the slope is -1. I think the same thing. If the slope is -1, let me think about that. Let's say the equation was y, and it is specifically -1. Y equals -x versus y equals -x plus 6. Is this the same thing as y equals negative and x plus 6 or negative x minus 6? Negative x minus 6 here, no, those aren't the same thing. So I think those are the only two cases. That's all I can think of. I think those are the only two cases. If the slope's -1, you would need the opposite w sign for that to work. So w equals 0, or if the slope is 1. No, not and or. I said or. So let's see how I'm saying this. If w is 0, even if the slope's 1, we're good. If the slope's 1, you're also good. I think that's all I need to say. One or the other. There we go. I think that'll work. All right, guys. I think that's it, and that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. If you did, listen, I forewarned at the very beginning of this video, this one's not for the faint of heart for IM1. The translation stuff to begin, the transformation stuff to begin with, pretty much could have wiped you out and said, nope, next video. I completely understand if that's the case. My obligation is to record each video as needed. Maybe you look back at this as an IM3 student and you're like, I totally understand this. Or maybe you still don't. Transformations can be an ugly nature for this. But the big ideas math textbook does not let up on them. They really, for some reason, I'm not saying they prioritize horizontal shrinks and stretches and stuff, but they seem to have them always precede the vertical ones. And vertical ones seem to make more sense. You'll see me do that as well for IM2 and IM3. Sometimes I turn horizontal ones into vertical ones whenever I can. You kind of heard me mouth that a couple times. It said, I'd rather do vertical when I can, and it makes sense to do it equally so. So guys, that'll do it for this one, and this is the end of the chapter. Next comes the Chapter 3 review and the Chapter 3 test and cumulative assessment. Check it out in the playlist whenever it is up, if it's up for you already. Thank you so much. Take care. I'll see you in the next one.